I was standing on the factory floor last month watching an Optimus prototype perform a task that, well, it should have been impossible. The engineer next to me, he was practically vibrating with adrenaline. He pointed at the robot's hands, the way the actuators adjusted with this sub-millimeter precision, and he whispered, "This is it. This is the end of manual labor as we know it." He looked like a man who had seen the face of a post-scarcity future. He even, he showed me a video on his tablet of the robot folded into a shipping crate, ready for the world. To him, the code was solved, the hardware was humming, and the revolution was essentially scheduled for Tuesday. But then the mood just shifted. A guy from the compliance department walked over with his thick clipboard, looking like he'd just stepped out of a 1950s tax office. He mentioned a new workforce impact assessment and a delay in the regulatory safety permit for the autonomous transport lanes. And just like that, the engineer's face just dropped. The adrenaline vanished, replaced by this look of pure, weary resentment. He didn't argue with data or safety metrics. He just gestured at the clipboard and muttered, "They're trying to kill the future with paper cuts." That sudden collapse from the high-speed velocity of a Type I civilization to the grinding halt of bureaucratic entropy, it was jarring. It's a pattern we're seeing everywhere right now. From robotaxis stuck in legal limbo to XAI clusters fighting for every single watt of power. It's not that the technology is failing, it's that the physical world is fighting back. We're witnessing a collision between the absolute speed of code and the suffocating weight of legacy systems. Are these 2025 delays a sign that the dream is over, or are they the final desperate gasps of a world that is terrified of what happens when we actually succeed? Okay, let's unpack this. That opening vignette, it really captures the central tension we are diving into today, the high-speed velocity of a Type I civilization. And for those unfamiliar, that refers conceptually to the Kardashev scale, describing a civilization that can harness all the energy on its home planet. That's the kind of leap the engineer felt he was making. Our mission today is to analyze these 2025 delays and bottlenecks across the entire technological frontier. We're talking physical robots, autonomous vehicles, and these massive AI compute clusters. We need to decide, are these delays a signal of genuine technological failure, meaning the science itself just isn't there yet? Or more provocatively, are they the desperate resistance of outdated systems and regulatory philosophy?
I think the material we've looked at suggests this friction it's structural, not incidental. It's the meeting point of this exponential digital progress and this very linear, very stubborn physical inertia. And we can really define this friction across three distinct but, intertwined fronts where the speed of code is meeting the resistance of the atomic world.
Yeah, we've mapped out these three fronts to guide our deep dive today. First, we're going to tackle the regulatory and political barriers that are actively stalling deployment, the legislative shackles on things like robotaxis. Second, we'll shift to the concrete physical supply chain and manufacturing limits hitting the hardware side, which is, the core challenge for programs like Optimus. And finally, we'll examine the colossal high-velocity battle for what's called sovereign compute and the urgent, unavoidable challenge of resource consumption being faced by these hyper labs like XAI. All right, so let's start where the political resistance is maybe the most tangible, in our cities, where autonomous vehicles are just struggling to get past the starting line. The anchor anecdote here involves an urban planner in San Francisco named Elias, who dedicated years to trying to integrate robotaxis.
Elias's story is, it's a textbook example of systemic stagnation. He spent three full years of his professional life trying to designate just a single short autonomous-only lane for a pilot fleet of robotaxis.
Just one lane.
One lane. And think of the irony there. The technical system, the sensors, the code, the reliability, he described it as flawless, like a ghost ship of innovation just ready to sail. But it never left the dock.
It was smothered by the bureaucratic process, and it wasn't one big no, was it? It was more like death by 1,000 cuts.
Exactly. A relentless, slow-motion parade of hearings, impact statements, environmental reviews. The technical system was ready, but the local physical infrastructure was held absolutely hostage by legal and regulatory frameworks that were fundamentally designed for the 1970s.
The process was engineered for slowness.
And this isn't just, local inefficiency. This individual frustration feeds directly into this monumental economic thesis, the Great Stagnation hypothesis. When economists like Tyler Cowen or Robert Gordon talk about this, they're arguing that the pace of fundamental progress, the kind that truly transforms daily life, has decelerated significantly since the 1970s.
I think the common mistake people make is they hear stagnation and assume that means no innovation. We still get new iPhones and new apps. So what exactly defines this slower progress we're talking about?
It's really defined by the type of progress. We're not saying progress is zero. What we're saying is that it's a dramatically slower rate compared to the revolutionary acceleration we saw between, say, the late 1800s and the mid 1900s.
Right.
That earlier period saw these simultaneous fundamental transformations.
Yeah.
Electrification, the internal combustion engine, modern medicine, radio, flight, mass production. That was civilizational uplift happening on multiple fronts at once.
Which brings us to Peter Thiel's framing, which I think is essential here. He really distinguishes the progress we do see from the progress we don't. He called it the atoms versus bits divide.
Precisely. We've achieved radical, often exponential innovation in the world of bits. That's information technology, software, networking, AI itself. I mean, you are carrying a device in your pocket right now that is arguably one of the most powerful computational tools ever conceived. The velocity in that space is just undeniable.
But the stagnation is concentrated in the world of atoms.
Yes, the physical sectors, transportation, which we already mentioned, energy infrastructure, housing and construction, and fundamental breakthroughs in personalized medicine. In these areas, the promises of the 1950s and 60s remain largely unfulfilled.
The list of these missing revolutions in the atomic world is pretty stark when you lay it all out.
It is. Take energy. Post-war futurists promised nuclear power would be too cheap to meter. We were supposed to be swimming in abundant clean energy.
Yet today, more than half a century later, nuclear power supplies less than 20% of U.S. electricity, and globally, it's still in the single digits as a percentage of total energy consumption.
And that revolution was fundamentally stifled, not by thermodynamics, not by the physics, but by politics and regulation.
And transportation is even more immediately frustrating for you as a traveler. I mean, we peaked arguably with the Concorde in the late 1960s. We had supersonic passenger travel.
We did, but it was shut down after less than 30 years and was never broadly accessible.
It's genuinely strange to think about. If you measure average passenger travel speeds today, they are effectively unchanged or maybe even slightly reduced compared to the speeds available 50 years ago. Your car doesn't go faster, your commuter train is often slower, and your flight across the ocean is no quicker.
And in medicine, while we celebrate these incremental victories, the fundamental challenges remain the same. Cancer and heart disease are still the top killers, unlike the prior era where infectious diseases were, essentially solved through antibiotics and sanitation.
Right.
The truly revolutionary potential of genetic engineering, things like CRISPR, is still navigating these extremely cautious regulatory waters, which prevents it from reaching its full life-saving potential quickly.
The systemic impact of this slowdown in the world of atoms is quantifiable, which is what makes Gordon's data so compelling, I think.
The figures are devastating. Gordon tracked the growth in output per hour, a key measure of productivity. That rate slowed from an average annual rate of 2.82% between 1920 and 1970, and then it just plummeted to 1.62% between 1970 and 2014. But the most alarming metric is total factor productivity, or TFP.
Okay, so tell us why TFP is the core metric here. Why does that number matter more than just output per hour?
TFP is designed to measure the efficiency with which capital and labor are used. Economists treat it as the residual. It's the part of growth that isn't accounted for by simply having more workers or more machines. It's the proxy for true technological and organizational innovation.
So it's the secret sauce, basically.
It's the secret sauce. In that earlier revolutionary era, 1920 to 1970, TFP grew at 1.89% annually. In every single decade since 1970, it has consistently fallen below 1%. That drop from nearly 2% to less than 1% means the speed at which we are innovating, fundamentally changing the economy, has been halved. We're operating on half speed compared to our revolutionary ancestors.
And that brings us squarely back to the regulatory philosophy that's applying the brake to this atomic world, and that is the precautionary principle. This principle is, in many ways, the philosophical engine of stagnation.
It really is. It's the ultimate expression of cautious inertia. The core idea is simple. If a new technology carries a potential or even a hypothetical risk of harm to the public or the environment, the burden of proof falls entirely on the proposer to prove it will not cause harm, to prove a negative.
Right.
If they can't meet that impossible standard of absolute safety, the deployment is limited or banned.
When you put it like that, requiring proof of no harm, it's obvious why it leads to government intervention based on purely hypothetical, often worst-case scenarios, even when there's no clear scientific evidence of an imminent, serious threat.
And the contrasting philosophy is what some in the sources call the innovation principle. This principle acknowledges that the vast majority of technological innovations actually benefit society, and the risks are usually modest and reversible.
So government's role is not to veto technology on speculation, but to encourage innovation while crafting targeted regulations to address specific, actual harms that arise during deployment.
Exactly. You don't halt the entire electric vehicle industry because one company's battery caught fire. You issue a safety recall on that specific battery, or you mandate better fireproofing.
Right, you solve the
You
problem.
solve the problem. But the precautionary principle is continually weaponized, creating these powerful veto points. And the sources show that the most common weaponization is rooted in job fear, not safety fear.
The fear of job displacement. That is perhaps the single largest human-driven drag on the deployment of autonomous systems. It's so powerful and deeply entrenched.
And it creates powerful political lobbying. We see proposals to completely ban autonomous vehicles based solely on this displacement fear. The New York taxi industry, which already suffered from ride-sharing disruption, urged a 50-year ban on self-driving cars. In Chicago, lawmakers introduced an ordinance to ban AVs outright, explicitly labeling them a job killer.
And it's not limited to the U.S. either, is it?
No, not at all. India's Minister of Road Transport cited unemployment as the direct reason they would not allow autonomous vehicles on their roads. The perceived social cost of job loss overrides the efficiency, the environmental, and the safety gains that the technology offers.
And if it's not an outright ban, it's these specific, costly regulatory requirements that basically function as an economic ban.
The New York example is so instructive. They required all autonomous vehicle testing to happen under the direct, physical supervision of state police, and the companies had to pay for the escorts.
Think about the cost curve there. If you're a startup trying to iterate quickly, having to pay thousands of dollars a day for state police supervision just to drive your test vehicle slowly around a track, it makes large-scale testing fiscally impossible.
Yeah, it's no surprise that testing in New York has been negligible compared to places like Arizona or California.
And this is the real cost of excessive caution. We see it everywhere.
Look at GMO bans. Despite decades of scientific unanimous consensus globally that genetically modified foods are safe for human consumption, speculative fears have led to widespread bans in Europe and parts of Africa.
And the unintended consequences are severe, and they often hurt the very people the policy was supposedly meant to protect.
Exactly. The cost includes higher food prices globally, which disproportionately affects the poor. It leads to increased greenhouse gas emissions because lower crop yields require farmers to clear more farmland. And most tragically, it limits the income and development of African farmers who could use improved, drought-resistant crops to raise their living standards.
So the precautionary principle often stands in the way of innovation that helps the public, precisely because it focuses on hypothetical risks rather than actual quantifiable opportunity costs.
That's it in a nutshell.
So if Part I showed us how regulatory paper cuts can kill a ghost ship of innovation, Part 2 shifts to the hardware. What happens when the engineers manage to beat the compliance officer, but the physical reality of the supply chain delivers the next bottleneck? We're moving from the stagnation of rules to the stiff, aging joints of the physical world, using the challenges facing the Optimus program as our guide.
This is where we run into what the sources call the Actuator Paradox, anchored by the story of Eris, a specialist machinist. Eris works at a facility that produces these hyper-precision components for robotics. He's essentially a craftsman from the future, capable of shaving titanium parts down to the single micron level to ensure the thermodynamic and kinetic efficiency needed for a walking, lifting humanoid robot.
He's making the joints that allow the future to move, but he described feeling trapped in a 20th century supply chain.
He spoke about the psychological toll, seeing these masterfully crafted, expensive, high-precision parts just sitting idle in shipping containers for months.
And the delay wasn't due to mechanical failure.
No, it was due to port entropy, logistics sluggishness, and critically labor disputes driven by union fears of a post-biological labor market. A workforce of robots that never clocks out, demands no wages, and never strikes.
It's a powerful picture of the cost disease affecting the atomic world. We have the desire for advanced robotics, which demands incredible efficiency and precision, but our industrial system itself is just sluggish and poorly adapted to deliver that complexity at scale.
And we see the consequences directly in the Optimus program itself. Despite aggressive targets, I think Elon Musk previously aimed for 10,000 units this year, the program has faced significant organizational setbacks. The head of the program, Milan Kovac, departed, and production has been delayed due to mandatory redesigns.
Redesigns that were necessary because of early component failure.
Exactly. The feedback from the factory floor to the suppliers was detailed, and it confirms that the gap is purely about physical mastery. It's not about the AI failing to recognize an object. It's about the materials and mechanics failing to execute the task reliably over and over again.
So what are some of these specific hardware challenges?
They're extensive. Things like joint motor overheating, which compromises performance and lifespan, low load capacity in the dexterous hands, meaning the robot can't consistently manipulate heavy objects, a short lifespan of critical transmission components, and ongoing limitations in battery life, which restricts how long the robot can actually work without a charge.
So while they have enough components to assemble over 1,000 robots, the source material notes that their current use is almost mundane, moving batteries in Tesla's own internal workshops.
And even when doing that simple task, they're operating at less than half the efficiency of a human worker. The economic case for immediate large-scale deployment just isn't there yet.
This leads us to the fundamental bottleneck for humanoid robot mass production, which is not what most people assume. It's not vision, it's not the high-level AI model.
No, the bottleneck is actuator precision and the rigidity of the physical supply chain that supplies these actuators.
This is the part that is often glossed over, but it's so critical. Why is actuation so much harder than vision?
Because vision is a computational problem. Actuation is a physics problem. Making a robot see is about processing data streams. Making it move like a human with the required force, speed, precision, and durability over a 10-year lifespan is vastly more difficult. You need highly efficient motors and extremely precise gearing mechanisms packed into a tiny volume.
And the core component enabling this is what engineers call harmonic drives, or strain wave gears.
These are arguably the most critical and complex components in modern robotics. They are precision mechanical reduction gears essential for joint movement. They convert the high-speed, low-torque output of a small motor into the low-speed, high-torque output you need for human-like movement, all while minimizing backlash and maximizing precision.
So if you imagine a watch, these are like the tiny, highly complex inner mechanisms, but built to handle incredible force.
That's a great analogy. And the difficulty in scaling lies in their production. Manufacturing these components requires specialized, ultra-precise grinding equipment that can machine complex gear teeth to sub-micron tolerances. And here is the choke point. This highly specialized equipment is produced by only a limited number of companies globally, primarily in Japan and Germany.
So the lack of supply is literally a physical constraint on the global machinery that makes the future possible. It's not a lack of interest or money or even design innovation. It's a lack of the specialized machines that make the machines.
Exactly. And on top of that, quality is paramount. It's not enough just to produce the gear. If the gear's precision is off by a single micron, that difference means the robot might not just fail a task. It might damage its own components or drastically shorten its operating life.
So you can make a gear that works for 6 months, but for industrial use, you need one that works flawlessly for 5 to 10 years.
And that pursuit of durability and precision severely constrains the already limited supply chain.
This challenge, this actuator paradox, it really reinforces the idea of civilizational drag. We're being held back by the system's inability to deliver this high thermodynamic efficiency at scale.
And that physical inefficiency is compounded by the bureaucratic resistance we discussed in Part 1. The sources refer to compliance reviews and labor pressure as entropy generators. Entropy generators, I like that.
They are actively slowing the inevitable transition to post-biological labor under the guise of workforce protection. But their real function is to generate organizational friction and just slow down the inevitable change.
And we see this played out in logistics technologies that are technically ready right now, but are facing these regulatory roadblocks purely because of job fears.
Delivery robots are a perfect, simple example. These small, sidewalk-based vehicles could dramatically reduce the costly last mile of delivery, which can account for, up to 28% of a product's transportation cost? The technology is simple, safe, and deployable. Yet San Francisco initially banned them entirely. And when the city finally relented and allowed a limited deployment, they imposed these excessive, punitive regulatory requirements.
Specifically, they required a permit and application fee of over $1,400 for a single robot, renewable every 180 days.
Wait, so a company needs to pay almost $3,000 a year per robot just to operate on the sidewalk?
That's right. And that fee structure effectively throttles deployment, despite the clear benefits. Cheaper and faster delivery for consumers and less traffic congestion.
And the same tension is delaying autonomous trucks, which offer even more massive safety and economic gains.
Autonomous trucking promises faster, cheaper long-haul service, which benefits every consumer good. And critically, the safety and environmental benefits are immense. Autonomous trucks don't get tired. They don't crash due to human error. Experts estimate the yearly crash savings in the U.S. alone could be around $900 billion.
$900 billion. That's a staggering number.
It is. Furthermore, the technology enables platooning, where trucks drive much closer together using sensors, which reduces wind resistance and dramatically cuts greenhouse gas emissions.
Yet this transformative technology is facing massive delays, primarily due to labor opposition.
The Teamsters Union, for instance, has actively opposed removing safety standards like mandatory rest periods that are completely unnecessary for autonomous driving. If you view the goal purely as workforce protection at the expense of productivity, safety, and environmental gains, then these delays are the logical, though tragic, outcome of applying the precautionary principle to the physical world. The atomic world simply cannot accelerate while being weighed down by these institutional fears.
Okay, now let's pivot entirely. If the physical world is constrained by regulation in this actuator paradox, the digital world is operating on a totally different timescale, one of radical, almost violent velocity. This brings us to our third and final friction point. The high-stakes battle for sovereign compute, centered on facilities like xAI's Colossus cluster.
The sources introduce a really fascinating philosophical dimension here. We have the perspective of a young site engineer in Memphis working on the Colossus construction. She described the facility not merely as a data center, but as a strategic exit ramp from a compliant, centralized digital theocracy.
That concept, a digital theocracy, is highly provocative. She felt that the centralized power of existing tech giants and regulatory committees was actively moralizing and throttling AGI development, attempting to apply that same precautionary principle to intelligence itself.
Her view was radical. The only way to counteract the societal drag and administrative stagnation is through raw, unrestrained computational velocity. To her, every kilowatt of power pumped into that cluster is a strategic strike against bureaucratic control.
It's an expansionist logic applied to computation.
Exactly. The pursuit of sovereign compute, this vertical integration to control the physical substrate of intelligence, is seen as the only rational path to secure the necessary compute moat for training these frontier-class models.
And the scale they are pursuing is, frankly, almost incomprehensible. xAI has an aggressive strategic target to have more AI compute than everyone else combined within 5 years. We're talking about an aspiration for 50 million H100 equivalent GPUs.
That is an objective designed to cement undisputed dominance in intelligence generation.
And the Colossus facility in Memphis is the physical manifestation of that ambition. By late 2025, that cluster achieved a historic milestone. 200,000 high-end GPUs operational, including 150,000 H100s, 50,000 H200s, and initial integration of the newer Blackwell chips. This isn't just large, it is a declaration of computational war. What's truly unbelievable is the speed of deployment. The first 100,000 GPU supercluster was set up and made operational in just 19 days. 19 days.
Jensen Huang, the CEO of NVIDIA, noted that setting up a supercluster of that magnitude coordinating power, cooling, networking, and the sheer physical hardware typically takes 4 years in a traditional corporate or governmental environment.
Wait, 19 days? You're telling me what usually takes 4 years? They did in less than 3 weeks.
The difference between 19 days and 4 years is the difference between velocity and entropy. That achievement is acceleration at its most extreme, proving that the digital world can, and does, move at the pace of code when it's unchecked by external resistance.
And that aggressive speed isn't just a point of pride, it's a core strategic maneuver, isn't it?
Absolutely. The Colossus 2 site, apparently, was mockingly labeled macro-hard on its roof, visible from space, underscoring the seriousness of this vertical integration and the desire to challenge the established dominance of Microsoft and OpenAI. They are attempting to build an unassailable strategic advantage.
And the ultimate justification for this massive hardware investment is the resulting breakthrough in model capabilities, the achievement of genuine deep reasoning capabilities in their latest models.
This scaling law, consistently more compute and more data lead directly to more intelligent models, has been validated by Grok 3's performance. It represents a fundamental leap beyond the earlier large language models, the LLMs, that were primarily defined by next token prediction, which is essentially guessing the next statistically likely word. Right. Grok 3 moves into true deliberation, and it manifests in these specific integrated features. One is its think mode.
This is essentially a chain of thought architecture, right? It's the AI visualizing its logical steps before committing to an answer. It simulates human-like reflection.
Exactly. It forces the model to articulate its reasoning process internally, allowing it to solve highly complex tasks that require multi-step logic, like PhD-level mathematics problems or extensive code auditing. It shifts the AI from being a rapid recall machine to a deliberate problem solver.
And the other feature that leverages this raw compute is deep search.
Deep search turns the model into an agentic researcher. It doesn't rely solely on static training data. It scans the live web and the X platform in real time, verifying sources, synthesizing live news feeds that are often only minutes old. This prioritizes freshness and verifiable citations over reliance on historical, potentially outdated data.
It gives the model a huge advantage in processing real-time dynamic information.
And the results confirm the power of scale. Grok 3 achieved a staggering 93.3% score on the 2025 American Invitational Mathematics Examination, or A.
And that's a highly competitive exam designed to filter the top math students. This really validates the central thesis of the accelerationists. Massive compute leads directly to powerful, deep reasoning intelligence.
However, this radical velocity ensures that even the world of bits runs headfirst into the physical world's constraints. The speed of digital progress quickly generated a massive physical backlash. The power crisis.
Okay, but a gigawatt of power. That has real-world consequences, right? It's not just a number on a spreadsheet.
Not at all. The Colossus facility, to operate at peak capacity, demands over 1.2 gigawatts of power. To put that into perspective for you, that single facility requires nearly half of the peak electrical demand for the entire city of Memphis, Tennessee.
Half the city's power.
That scale is unprecedented, and it instantly strains legacy infrastructure. Because the local grid was simply not designed to absorb that kind of sudden concentrated load, XAI had to deploy creative, temporary but controversial solutions. They deployed dozens of mobile natural gas turbines and 168 Tesla Megapack batteries to stabilize the power load and ensure uptime, bypassing the local utilities limitations.
But this immediate physical response, this necessity for raw energy, it instantly sparks societal friction and legal challenges.
That's right. In mid-2025, the NAACP and the Southern Environmental Law Center, the SELC, filed an intent to sue the operation under the Clean Air Act.
And the core of that challenge was environmental justice.
It was. They alleged that the facility's reliance on the mobile methane turbines was creating a major concentrated source of nitrogen oxides and formaldehyde emissions. These pollutants were disproportionately impacting the neighboring community of Boxtown, which is already an underserved area facing high rates of asthma and cancer.
This incident is the perfect microcosm of the systemic conflict we are analyzing. On one side, you have the radical pursuit of exponential technological progress, aiming for a post-scarcity future powered by AGI.
And on the other, that radical velocity immediately generates concentrated environmental and social costs, in this case, localized pollution, that the legacy system and the communities within it are simply not equipped to absorb without conflict.
The philosophical divide is just so clear.
It is. You have the accelerationist logic, the pursuit of sovereign compute as a way to violently solve the world model problem-viewing code as a strategic weapon against bureaucratic control.
And the ultimate goal is not just a faster AI. It's bypassing the stagnant administrative state entirely to reach the energy milestones of a Type I civilization. They are arguing that the only way forward is to scale energy, scale computation, and outrun the bureaucratic entropy that has been artificially slowing progress since the 1970s. So we've tracked the friction across all three fronts: the regulatory stasis suffocating robotaxis, the supply chain physics constraining Optimus, and the explosive velocity and resulting power crisis of Colossus. What is the final synthesis of this comprehensive conflict?
I think the core finding is undeniable. The fastest-moving technology, AI compute, has decisively validated the power of scaling. It's delivered profound reasoning breakthroughs like Grok 3, effectively securing the foundation of a new industrial age. However, the direct application of that powerful new intelligence in the physical world, whether through fully autonomous robotaxis in cities or versatile Optimus robots on factory floors, is being systematically suppressed.
And the suppression is entirely a product of outdated regulations and physical supply rigidities that were engineered for the slow, linear pace of the 20th century. The delays we're seeing across every technological frontier are not evidence of technological failure. They're symptoms of a systemic structural inability of our legacy institutions to integrate rapid change and efficiently absorb its necessary localized costs.
And if we look back at the Great Stagnation, the problem facing us is not that we have run out of technological low-hanging fruit. The problem is that the immense collective weight of legacy compliance, institutional inertia, and bureaucratic entropy has artificially raised the height of the physical world's hanging fruit so high that we can't reach it without extraordinary, often controversial effort.
The solutions are technically feasible. The resistance is cultural and political.
Exactly.
This brings us back to the civilizational choice that the source material really forces us to confront.
We must reject the fear-based precautionary principle, which often functions as nothing more than institutional inertia masquerading as prudence. Instead, society must embrace the radical velocity and the massive scale required in compute density, physical production, and energy utilization to accelerate humanity into an era of true abundance, knowing that any perceived compromise in speed is not caution, but merely a path toward systemic decay.